This is Algebra 2 Honors. This is our test, says quiz here, but test over the first module, analyzing functions. And there are a total of 15 problems here. For 1 through 4, use the graph of quadratic function fx equals negative x squared minus 2x plus 3. 1. Write the domain of the function as an inequality using set notation and interval notation. Well, being a quadratic function, part of the family of polynomial functions, the domain of those functions is all real numbers, which in inequality form is going to look like this. X is going to be greater than negative infinity, but less than infinity. So that's going to be our inequality notation. And our set notation is going to be very similar to inequality notation. X such that, and then we can just write in the same format here. X is greater than negative infinity, but less than infinity. And then lastly, we're going to have an interval notation, which is going to take the form open parentheses, negative infinity, comma, infinity, and close parentheses. So that would be it. Inequality, and set, and interval. And we've been doing that, doing these notations long enough, should be pretty easy. Write the range of the function as an inequality using set notation and interval notation. Well, we have some choices here. You can write this as y, and we have a maximum value of y. So you can write this as y is less than or equal to 4. That's one way to do it. Or you can write this as a negative infinity is less than, there we go, y, which is less than or equal to 4. And in our set notation, you can write that as y such that y is less than or equal to 4. Or y such that y is greater than negative infinity, but less than or equal to 4. To me, these things are equivalent. And finally, interval notation, you can write that as open parentheses, negative infinity, comma 4. And are we equal to 4? Yes, we are. So we're going to close here with a bracket. So there we have inequality, set, and interval notation for problem 2. Describe the end behavior of the function. Well, as x approaches or goes toward infinity, f of x does what? Approaches, well, we're going to be going down on either side, so we're going to be approaching negative infinity as x approaches infinity. And then as in end behavior, we got to look both ways. As x approaches negative infinity, f of x approaches also negative infinity. So this is an odd, even numbered function, which means you're going to start low, end low, or start high, end high. And so these end behaviors are going to match up no matter which way we're going, to the right or the left. 4. What is the range of the function if the domain is restricted to negative 3 comma 1. So we can go ahead and look at x equals -3. And if we go to -3, I'll go to right here, -3 along the x-axis, and 1 will go right here. So if we restrict our domain between these two values, what is going to be the corresponding range? Well, I'm just going to box this off like this. So in this instance, our range is going to be lower limited by 0, yet upper limited by the maximum of this parabola, which is 4. So that's going to be our answer to problem number 4. 5. A student reads 3 pages of a book every 5 minutes for an hour. Okay, so you have 3 pages every 5 minutes for an hour. Well, if we want to go ahead and we can write it in terms of minutes as f of x equals 3/5 x. That's one way of doing it. And we could also do this in hours, but we're going to do this for an hour. Well, that would be our domain would be in minutes, 1 hour, 60 minutes. We could write our domain as 0, 60. And what would be our corresponding range? Well, if we plug in down here f of 60, what are we going to get? We're going to get 3/5 times 60, which is going to be 90 over 5. And how many times does 5 go into 90? Well, 45. No, 40. 36. 45 divided by 2. Is that right? I don't know if that's right. Because 90 divided by 5, I'm not getting 36 for that. You know. Oh, that's 180 divided by 5. No wonder, yeah. My arithmetic is off. So, yeah, 30 times 60 is 180. And 180 divided by 5 is going to equal 36. So we'll say range goes 0 to 36. Now, alternatively, we could have changed this into hours instead of minutes. In terms of minutes, this is what it's going to be. This is your function. And you have a domain and range here. Next. Oh, I forgot. This could also be equivalently put in as f of x equals 0.6x. Because decimalized, that's what 3/5 is going to be, so that's a possibility as well. Next, 6. The graph shows a function that models the number n of seniors from a high school accepted a 4-year university's function time t in years over a 10-year period. Is the function increasing on each of these following intervals? Well, between 0 and 2, there's 0 and 2, it looks like the function is going up there as best we can see, you would answer yes for this interval. Next, between t is 2 and 6, well, here between 2 and 6, the function is overall headed downward. So we're going up in this initial interval, then we're going down. So are we increasing over this next interval? No, we're not. We're in fact decreasing. And the last interval is 6 to 10. Well, between 6 and 10, the number of seniors is on the increase. And so we answer part C, yes. Should have been quite a simple problem. The table shows some values of the following function. Is the average rate of change of the function positive over each of the following intervals? From 0 to 1, yes or no? Well, from 0 to 1, we are increasing from 80 to 100. Is that an increase? Yes. Yes, it is, which means positive. So yes, between 0 and 1. Next, between 1 and 2, well, between 1 and 2, we are going down from 100 to 40. So no, we do not have an increase over this second interval. C, from x equals 1 to x equals 3. Now we're comparing this value here and this value here. Oops, no, excuse me, 1. So it's 1 to 3, so it's this 100 compared to this 20. Are we going up? No, we're not. We're going down. So we say no for part C. And finally D, from 3 to 4. Well, from 3 we're at 20, and 4 we're at 40. So are we positive between these two? Yes, we are. So positive rates of change. Now, one thing you can do also on this that could be helpful is if you graph this here, you might be able to see that 0, 1, 2, 3, 4, and just put the values up here. 80, 0, you have 80. At 1, you have 100. There's 100 there. At 2, you have 60. At 3, you have 20. At 4, you have 40. So you can just kind of look at it this way to make it a graphical thing. 100, 60, 40, 20. Next, problem 8. A function is positive over the intervals, and this is a set notation. Now this is one that I could just tell from looking at the people working on the test questions I got during the test that this one was a stumper for a lot of students. Let's just go over to the draw an XY coordinate plane. And so the function is positive over the intervals from x equals -2 to x equals 0. So here at -2, so between -2 and 0, the function is positive. So we go up, so the function will look something like this. Does it look exactly like that? We don't know. And then also between 3 to infinity, so at 3, and then we go for infinity, so 3, we're getting positive, and we're going up for infinity here. And so, do we know about anything less than -2? No, we don't. Okay, it could be something like, in fact, I'm gonna dash line it. Could be something like this. And then between 0 and 3, we could look something like this. But what are the zeros of the function? Well, the best we can tell, we have zero potential zeros at -2, 0, 3. And say x equals -2, 0, 3. So the challenge of this one is that it requires a little imagination, just kind of see what's going on. And a sketching like this can be quite helpful. Next 9, find the find the equation of the line of best fit for the data in the table. And so for this, one way to do this is to go to your graphing calculator. I have a TI 84 CE calculator. Go to Stat Edit, and then enter the values here in the table, which are 1, 2, 3, 5, 6. So 1, 2, 3, 5, 6. And then over here on the output, we have 5, 7, 9, 13, 15, 5, 7, 9, 13, 15. So we have them all. And to find the linear regression, we go to Stat Calc 4. So we get A equals 2, B equals 3. So Y equals 2x plus 3. So our equation is going to be Y equals 2x plus 3. Now I do want to show you one more thing about this. You have to notice this morning. We go over here and put in equation 2x plus 3, and we turn on our plot here, and I want to get the right zoom window. We'll go from 0 to 8. Oops. 8, and go by ones. And Y minimum, we can start at 0. We'll go up by 1 again. Go up to 20. What is this thing going to look like? Graph. You see that all 5 points are directly hit. So line of best fit. Now that's the exact correlation. Next 10. Describe how to transform the graph of f(x) equals x squared to obtain the graph of the linear function g of x equals -3 f equal x squared plus 1 minus 5. Well, all these numbers do different things. Okay, this negative sign will reflect graph over or about x-axis. Okay? And then the next thing is the 3. So this is going to be vertical stretch by factor of 3. And then we have this x squared plus 1. Well, x plus moves to the left, and x minus to the left. So x plus moves to the left. So translation, one unit to the left, and then finally this minus 5 is translation 5 units down. Now, just from what I could see in some of the tests was, I don't know what happened here. I guess we need to work more on this. But you can take these out of order, possibly. It's you can translate first before turning upside down. But if you translate up, you're no longer going to be reflecting graph about the x-axis. You're going to be reflecting graph about y equals, in this case, -5. But so doing it in this order that I did it here, I think makes it easier. So, but coincidentally, you just work from left to right. The negative sign, that's this thing here reflected by the x-axis. The number 3, that's a vertical stretch. This +1 means translate 1 unit to the left, and at the very end, this -5 will translate 5 units down. So this is related to what we're going to be doing in the next problem. The vertex form of a basic quadratic function is this: f of x equals a times quantity x minus h squared plus k. And the a has to do with the vertical stretch or compression of the parabola. This h and k deal with, well, h moves the quadratic function left to right. The k will move the graphical quadratic function up and down. Let's go to this next one, which, number 11, is very much related. I'm going to rewrite the formula I just wrote earlier, the vertex form, f of x equals a times quantity x minus h squared plus k. See if I got the same thing there. Yeah, same thing. And so we can look at this like we have a coordinate plane right here. So that'd be an x-axis, and I'm drawing a vertical axis here, which will be a y-axis. I'm getting that a little off. I'm going to just move that over. There we go. Okay. Yeah, it still is in that mode. All right. Say xy right here. And our vertex is going to be the point h comma k. And here we have 0 comma 3. So 0 comma 3. So h is equal to 0. K is equal to 3. And now we're going to take one of these other points and use it. So we have h and k already. We just need to find our equation. We need to find what a is. So we're going to take 19 and substitute it for f of x, and 24, substitute it for x. And then when we work everything out, we're going to see what happens. We already know that h equals 0, and we know that k is equal to 3. So let's go bring this down here. We have 19 is equal to a, which we don't know yet, and then x is equal to 24, and h is 0, so we can just square that out and put plus 3. And now it's really a matter of solving for a. So if we subtract 3 from both sides of this equation, we get 16 is equal to 24 squared times a. And so a, therefore, is going to be 16 divided by 24 squared. And we can do that in our calculator here. So we get fraction alpha y equals enter 16 divided by 24 squared. So we get 1 over 36. So 1/36. So what is our equation going to be? What's a quadratic function? I said an equation. We're going to have f of x equals 1/36, and we're going to have x squared plus 3. So that should be it. The only thing we need to do as far as the function goes, or should do rather, is that we can graph this and see that all the points are met. So if we go to 136th, x squared, and we add 3 to that, and if we graph, don't see a whole lot, you can go through the points. One thing you do is go to table view. If we at it was negative 24, right? So we get 19. So negative 24 comma 19. The 0 comma 3, our y-intercept should be there. Yeah, we have that. And then if we get 24 comma 19, we know that we're exactly where we need to be. Yeah, 24 comma 19. Now last, so this is going to be our function. We checked it. That's good. The last thing we're going to do is find the function's domain. Well, our domain is going to be the allowable input values. So domain is going to be greater than negative 24 to 24, and it really doesn't say what mode to put this in. I used interval notation here. You could have used set notation, inequality notation, right? Could have said x is greater than or equal to negative 24, but less than or equal to 24. That would have been also okay. Next, 12. Find the inverse function f negative 1 for the function fx equals negative 1/2 minus 3. So I talked in this class about four-step process of finding the inverse of the function. First step is to change f of x to y. So I'm going to change f of x to y. So we have y equals negative 1/2 x minus 3. Next step is switch x and y. So we have x is equal to negative 1/2 y minus 3. Next step to solve for y is adding 3 to both sides of this equation. And if we do that, we get negative 1/2 y is equal to x plus 3. And now to solve for y, if we multiply this whole, what's going to cancel out this negative 1/2? Well, negative 2. Negative 2 times negative 1/2 equals 1. So we're going to get y is equal to negative 2x, and then negative 2 times 3 is going to be minus 6. So negative 2x minus 6, we can check it using the composition of functions, a lot of different ways. We can take the way we did a lot in classes this way. You go to y equals, you say, okay, negative 1/2 x minus 3. So we have that in graph. I'm going to go zoom 6. And then the inverse, well, we can go about the line y equals x. I'm going to make this black one, y equals x. So the correct answer is going to be a reflection about this line y equals x. And to get our correct answer we had here in red, we had negative 2x. And that was minus 6. See what that looks like? That's what we got here, right? Yeah, negative 2x minus 6, that looks good. graph. And so we don't see if we go to zoom square, we're going to get a better proportionality to see that line y equals x. So these are the red one and blue ones are reflections about this line y equals x. Hope you can see that's the case. And the last thing we're going to do is find f negative 1 of x is equal to negative 2x minus 6. So that's going to be our answer here. Okay, number 13. Choose true or false for each statement about inverse functions. A, if an inverse function contains the origin, then the inverse contains the origin. Yeah, because if you have the point 0, 0, you know that characteristic of an inverse function is x becomes y and y becomes x. And so if 1 contains the origin, the inverse is likewise going to contain the origin when x's and y's switch. So this is going to be a true statement. Next, the inverse has 3 x-intercepts, and then its inverse has 3 y-intercepts. And we didn't talk about this one specifically, but we said that the domain of a function is the range of its inverse and vice versa. When you switch x and y's, that's going to be exactly the case. So we can demonstrate that's the case in many different ways. See, if the slope of a linear function is less than 1, then the slope of its inverse function is greater than 1. Well, here we have, let's go look back here, okay? Let's look at number 12. We have the slope of a function. Is that greater than 1? Oh, it's less than 1, right? It's less than 1. So the slope of its inverse, is it going to be greater than 1? Well, the slope of its inverse in this case is negative 2. So this one here, problem 12, is a counterexample that proves, that shows that for part C, that's false. If the function is 1 to 1, then its inverse is a function. That is true. A 1 to 1 function, or at least the graph of a continuous function that's 1 to 1 would be, there's an xy coordinate plane, would be something like this, right? So therefore, its inverse would be a function like this. So for 1 to 1, you're going to have something called the horizontal line test. So that's that. 14, monthly cost C in dollars, cell phone carry charge of C equals 0.05 M plus 45, where M is known as. Find the equation for the inverse function. Well, what we're going to do is we have this function right here. I'm going to take it to the right, and we are going to switch the variables. So we're going to say minutes equals 0.05 cost plus 45. Now we're just going to solve for C. So if we subtract 45, we're going to have 0.05 times the cost is equal to M minus 45. Now if we divide by 0.05, divide everything by 0.05, so we'll have cancellation. C is equal to, now 1, and I'll show you this, and I hope you know this number sense-wise, but 1 divided by 0.05 is equal to 20. Okay? So let's go here, say, so 20M. And then we have negative 45 divided by 0.05. we get negative 900. So this is going to be our equation for its inverse function. And interprets meaning that the cost you can say cost depends on minutes on minutes used. That's a meaning. And what's going to be the domain and range? Well, cost has to be greater than or equal to 0. Minutes has to be greater than or equal to 0. You can't have negative values, in other words. Domain and range. So another way to say this is domain and range restricted to non-negative numbers. To non-negative numbers. And number 15. Write the inverse of the function as a set of ordered pairs. Well, one thing you can do first of all is you can take and write these coordinate pairs as they exist here. So this first one is going to be negative 4, 3. Okay, next one is negative 3, 2. Next one is negative 1, 4. One on the right is 1, negative 2. And then we have 2, negative 4. And finally we have 4, negative 3. And then we can take all these and these ones below are going to be the inverse of the ones above. So we have negative 4, 3 becomes 3, negative 4. Then we have 2, negative 3. We have 4, negative 1. We have negative 2, 1. We have negative 4, 2. And finally we have negative 3, 4. And we could say as a set, right? And we could say in brackets like this. So we would say inverse of the original. Then plot the ordered pairs for the inverse on the grid. So 3, negative 4. So we go 3, negative 4. We have that here. We have 2, negative 3. So 2, negative 3 will go here. Again, we are reflecting about this line y of x, right? Negative 4 comma 3 becomes 3, negative 4. Oops, I got that wrong, didn't I? 3, negative 4 is going to be this guy right here. Next one, 4, negative 1, so we get 4, negative 1. Then we have negative 2, 1, so negative 2, 1. Then we have negative 4, 2, so negative 4 comma 2 will go right here. And the last one we have is negative 3 comma 4, so negative 3 up 4. So just all these points here are plotted. So that's it. That's all there is to it. Hope it's been helpful to you. As always, make sure I'm not missing anything here. That's going to be it, really. So that's it. As always, good luck, and thanks for viewing.